All right, 7.3, logarithmic functions. We're going to find out that logs are actually the inverses of exponents. So that's kind of the road that we're going down. So we kind of open up with this question that says, how many times would you have to double the number 3 to get to 768? All right, so how many times would we have to double the number 3 to get to 768? You might start it off in your head, and you might go, well, 3, 6, 9, 18, 36, 72, and then it's like, well, that's going to be a little while. So another way could be, well, let's try to write an equation, just like we've done in the previous couple sections, because this is growing exponentially. So if we take the number 3 and we double it, and we're asking ourselves, how many times, so we don't know the exponent, how many times will that get us to the number 368? Well, in the next 3 or 4 sections, we're going to learn how to solve an equation like this using logarithms. So it's basically whenever you don't know the exponent. Now with a graphing calculator, we could kind of cheat, and we could kind of look and see how many times that is by simply typing in, y equals 3 times 2 to the x, and then we could kind of look for this value in the table. We could see what x would get us to 368. So I'm not going to do that right now, but that's the type of question that logs can kind of help us solve. So basically, a logarithm is an exponent with a certain base that gives a value. And we can write exponential equations as logarithmic equations and vice versa. We can go back and forth. So this is kind of one of the more important pieces of today. So I'm going to go down here, and the first batch, I give you an exponential equation, and we need to rewrite it in logarithmic form. So here's how it's going to kind of go. So logarithmic form, the 6 is what we're kind of after. So I write it like this. I would say log base 2 of 64 is 6. So notice that in logarithmic form, the answer over here, the answer is the exponent. That's what we're after. That's what we're trying to figure out, and that's going to be our x in a lot of the equations later on in this chapter. This 2 right here, this is the base, all right? And then the 64 is kind of the answer from exponential form. I know sometimes people refer to this as it's kind of like a circle. So if you think about it so let's say that we have, b to the x equals a, let's say, some sort of answer. Well, how you can write that is it kind of goes into a circle. So it kind of goes, well, I guess if I do it as a log, it would kind of go into a circle, but you would write this as log base b a equals x. So you can kind of see that you kind of have this relationship that kind of goes in a circle where you have the base on the bottom, your exponent, and then your answer over here. And it just takes a little bit of practice to kind of get the pattern down. So let me kind of move down, and we'll do some more, and hopefully more with pattern recognition, you'll kind of see what's going on. So on this one, we're going to say log, the base is 4, because this is the base. The exponent is 1, 4 to the first power is 4. So on this next one, 5 to the 0 power, so if I have a base of 5 to the 0 power, well, that equals 1. This one's a little trickier. So my log is base 5, because that's the big number. But then what do I kind of come up with here? Well, this is where my 0.004 goes. And this is where the negative 2 goes, because that's the exponent. And later on, we're going to do some mental math and try to figure some of these out. On this next one, this would be log base 3 of 81 equals x. Now this is one that we're actually going to solve in our head kind of later on down below. So be ready for that. So when we slide down, let's go the other direction now. Let's we have exponent form. Let's go over here into log form. So all right, and it looks like I screwed up here in my notes, so you're going to have to do some scribbling out here. So these guys were actually, they're not in logarithmic form, they're in exponential form. So just scribble this out, and we'll kind of redo it here. So let's try to do, if it has log base 10 to the 1,000 equals 3, so that's log form. If I want to write that in exponential form, remember this is the base, this is the exponent, and this is the result, or the answer. So it kind of plays that little circle game when you're kind of going from log form to exponential form. So that's kind of the little pattern that plays out. Let's do a few more. We don't have to do all 5, but maybe I'll do like 4 of them or something. So we have log 5 of 0.25 equals, or not 0.25, 625. Can't read my writing here. Equals 4. So if I was going to write this one using exponents in exponential form, I would say, hey, 5 to the 4th equals 625. Let's do something like log base 9 of 9 is 1. Well, that looks kind of weird, but if you write it in exponential form, 9 to the first power equals 9. So it looks pretty good. Let's do something like this. Log base 15 of 1 equals 0. Well, that's logarithmic form. In exponential form, 15 to the 0 power equals 1. And that's true, because anything to the 0 power equals 1. So we can move from exponential form to log form and vice versa. That's a skill that you need to be able to have. You've got to be able to move fluently back and forth. Here at the bottom, it says, since a log is an exponent, the rules of exponents apply. And I basically just showed you 2 examples of these, the very last 2 we just did up above, in that if you see that the log and you see these 2 numbers are the exact same, you know that it's got to equal 1. So even if I just said like, hey, what's the log of 5 of 5? What's that equal? Well, you could do that mentally because you're like, well, that means 5 to the what power, because remember this is the exponent, will give me 5. Well, the only way that can happen is if the exponent is 1. So whenever you see these 2 are the exact same, you know that that needs to be 1 over there. And then the logarithm of 1. So it doesn't really matter the base. So I could have log of anything. The only way to get a 1 is if you have the 0 for the exponent. So regardless of what number is down here, if I rewrite it in exponential form, 7 to the 0 power equals 1. It's still true. So those are just a couple properties. I mean, you don't have to memorize them. As you do them mentally, they'll just kind of make sense, but those are a few special properties. All right, a logarithm with base 10 is often called the common log or common logarithm. So a lot of times if it's a base 10, they won't even write a base. There'll be no base written. So we can assume that it's base 10. And a lot of times you can do mental math on these. So for instance, if it just says log of 1,000, it's really meaning log base 10 of 1,000. And we could answer this question, we could figure this out. Because if we write it in exponential form, it's basically saying 10 to the what power gives me 1,000. And I'm like, oh, that's 3. This one might be a little bit tricky. Log base 4 of 1/4, well, 4 to the what power gives me 1/4. And this one might be a little tougher because, 4 to the 0 is 1. 4 to the 1 is 4, but we got to go even smaller than that. So that usually tips you off when you're going to have a negative exponent. And this is actually -1. Because think about this right here. When you do 4 to the -1 power, it's really 1 over 4 to the +1 power. So sometimes your logarithm over there is actually a -1. You can have negative exponents, that's fine. This next one, this is asking 3 to the what power is 81. This was the one I referred to in the beginning of the notes where it said 3 to the x is 81. Well, that's 3 to the 4th power. Ooh, this one's a little tough. I don't see a base, so I know it's 10. And I'm like, 10 to the what power is, well, I might want to write this as a fraction. You know, this is tenths, hundredths, thousandths, 10,000ths. That's 1 over 100,000. So then I kind of have to ask myself, well, I know it's going to be a negative, but what negative exponent is the same, you know, negative something. But then I'm really asking myself, well, 10 to the what power gets me to 100,000. So I think I would multiply it by 2 would be 100, 3 would be 1,000, 4 would be 10,000. I think 10 to the 5th is 100,000. So 10 to the -5th is 1/100,000th. So this would be an answer of -5. So that's just doing a little bit of mental math with logarithms. And we'll do some more to get some drill and kill, some practice. All right, well, let's do some graphing. It says use the given x values to graph each function, then graph its inverse. So first let's make a table and let's graph these. So here's my function. I'm going to kind of write it over here. Y equals 3 to the x. And I'm going to make a table. I like my tables going up and down rather than side to side, so I'm just going to do it that way. And they tell me what x's to pick. They want me to go from -2 to 2. So -2 to 2. So let's do this. Well, 3 to the -2, that's 1 over 3 squared, so that would be 1/9. 3 to the -1, well, that's 1 over 3 to the 1st, or 1 over 3. Anything to the 0 power is 1. If I put a 1 in there, 3 to the 1st power is 3. 3 squared is 9. So I can now graph that function. So I can be like, all right, -2, we're at 1/9 with this way down here. And what happened there? Let's get rid of that little joker. All right, let's get this back on there. So -2 is to the 1/9. -1 is to the 1/3. 0 is at 1, which is a pretty common point. 1/3 over 2, and we're already up to 9, and we're going to fly off our grid pretty quick. So it looks like this one. Straight up like that. So definitely exponential growth. As I'm growing faster and faster and faster. So I've graphed that. Then I have to graph the inverse. So the inverse here, which f of 1 to the x, basically I'm just going to switch all of these values. Just going to kind of flip them around. And so when x is 1/9, I am at -2. When x is 1/3, I'm at -1, 1, 0, 3, 1, and 9, 2. I believe I flipped everybody, right? So let's graph that. So over 1/9 down 2, over 1/3 down 1, 1, 0, 3, 1, and 9, 2. All right, and this goes. And you'll notice a couple things that, you know, this function over here, the original, this one had a horizontal asymptote. Remember that line that it approaches but it never crosses? So that had a horizontal asymptote at y equals x, right down here at the bottom. there's for the blue function, there's an asymptote right there. But then when you look at the red function, there's actually an asymptote at the line y equals 0, because it's never going to touch that line. And just like it's supposed to do, it's symmetrical. It's symmetrical across the line y equals x here. You got that line right there, that fold line. A graph and its inverse should always be symmetrical about that line. So it actually did what it was supposed to do. So it says describe the domain and range for each of these. So let's just do the domain of the blue one. The domain of the blue, well, that's what can the x's be. And I don't think the x's are restricted at all. So I think the x can be anything. So I think for the domain, it would be all real numbers. And for the range, what can the y's be? Well, the y's have to be greater than 0. The y's have to be greater than 0. Not equal to, because we're never going to touch 0. We have an asymptote. If you're using interval notation, you would basically go from a soft 0 all the way to infinity. All right? For your range there. Now, over here on the other function, on the inverse function, when I do the domain, well, the domain are what x's are they? Well, our x's don't go past 0. So they actually, our x's, have to be greater than 0. They're never equal to it. So again, if I wanted to do interval notation, I could do it that way. And then the range can be anything with the red function over there. The range is going to go all the way down. It's going to go up. So it could be all reals. The big thing you need to understand from this is that the domain and range flip-flop from the original function to its inverse. All you really have to do is just reverse these two, and they end up being the inverse's domain and range reversed. All right, next one. So this one, our original function, I'll do this in blue again maybe. Our original function is y equals 0.8 to the x power. And they tell me the values they want. They're pretty specific here because some of them are pretty nasty. Decimals, -3, 0, 1, and 4. And I know some of these off the top of my head. Like when x is anything to the 0 is 1. 0.8 to the first is 0.8. 0.8 to the fourth power. So I'm going to punch in 0.8 to the fourth power. 0.8 raised to the fourth. That's going to be roughly 0.41. 0.4096. I'll just call it 0.41. 0.4 is probably as good as I can get on this graph. And then 0.8 to the negative third. 0.8 raised to the negative third. And in my calculator, it says 1.95. Just double check that. Yeah, 1.95. All right, so let's graph those. So when x is -3, which is going to take me off the grid a little bit, I'm at 1.95. So I'm almost at 2. When x is 0, I'm at 1. When x is 1, I'm at 0.8. When x is 4, I'm at 0.41. So I'm kind of getting smaller and smaller. And so this one's going to kind of come flying down. Going something like that. I know I'll never go to 0. But I'll just keep kind of approaching it further and further. And then if I want to do the inverse, if I want to do inverse of x, well, I'm going to flip those two around. And I'm just trade places here. And let's do this. So over almost 2, down 3. over 1 at 0 over no, doggone it. Somehow it's like pasting. If I hold my pen too long, it like pastes that feature in. So that's kind of annoying. So now I got to do my points again really quick. All right, got everything drawn back here. Over 0.8 is up 1, and over 0.41 is up 4. So this thing's kind of doing one of these numbers. And if you notice and you look at it, it should again be symmetric across that line, which it is. I'm not the greatest drawer, but I think you can kind of see that that's what it does. So let's go back and let's hit the domain and range for these because they are functions, so they do go forever. So it looks like for the blue on the original, the domain looks like x can be anything. X could be all reals. The range, it looks like we are not going to go below 0. So this is not very interesting. Pretty similar to the last one. So I'm just going to flip-flop these. And we should be good to go. All reals. All right, now we move on to a chemistry example here. Rodriguez will be happy about this one. So it says, formula below is used by chemists to test the acidity of rainwater or the concentration of hydrogen ions, which is H positive there, H plus. Acidity is measured in pH, given by the function that the pH is equal to the opposite of the log of the hydrogen ions. And this H plus, what goes in there? It represents the hydrogen ion concentration in moles per liter. So I remember mole is like a really huge number. I want to say something to do with Avogadro's number, but my chemistry could use some brushing up on. But it says find the pH of the two locations below. So in central New Jersey, they measured it, and the hydrogen, this input, came out to be a bunch of zeros, 316 moles per liter. So what I need to do is I need to put that into this equation to calculate the pH. So somehow we measured the concentration of the hydrogen ions. We had that many moles per liter. So the pH should be negative log of, and notice there's no base here, so this must be base 10. So let's pull up the old graphing calculator and let's see what shakes out. Fire this thing up, turn it on, and quit out of this screen. All right, so now we're just in our normal nice screen. So now I got to do logs. So a couple different ways to do log. We have a key right down here. If you go in the left-hand column, right next to the 7, there's log. And we needed let me see, there's 4 zeros. 1, 2, 3, 4, 3, 1, 6. Enter. 4, but it's the opposite of that. So I didn't put the negative in front. So it's the opposite of negative 4.5. So it looks like the rainwater in central New Jersey is about 4.5. All right, that's a pretty low pH. All right, that's really low. That's pretty acidic, actually. Maybe here in a second I'll pull up a little scale so you can kind of see alkaline and acidic. But that's 4.5. If you go into central North Dakota, so let's kind of slide our calculator over here so we can see. If I go to central North Dakota, it turned out to be, and that looks like the exact same number. So it looks like screw up number 2 in my notes. This one looks like 1, 2, 3, 4, 5, 6. 6 zeros and a 9. All right, so we're going to tweak this. Looks like I copy and pasted, and I didn't change it. So in Central North Dakota, it's 0. Looks like 6 zeros. 1, 2, 3, 4, 5, 6. And then there's a 9 at the end. All right, so much different collection. So let's see what that shakes out to be. 6 zeros with a 9 in it. Go back to my calculator. I'm going to do this one right. Negative log or opposite log of 0.1, 2, 3, 4, 5, 6, 9. Enter. 6.04. All right, so a much different pH for this one. Pretty close to 6.0, 6.04. So two different parts of the country, two completely different rainfalls as far as the acidity. Let's just double check. I'm going to pause the video and I'm going to come back with a little chart that shows you acidity and alkalinity. All right, so I found a pretty cool chart here that actually breaks down these numbers. So as you go towards 0 on the pH scale, that's acidic. As you go to the top, that's alkaline. It looks like neutral is 6. So, you know, when we were looking at Central North Dakota and we were coming in at 6.0, we're right here in this nice area of clean rain, healthy lake, all that type of good stuff. And when we were looking at New Jersey, central New Jersey, that was coming in at 4.5, which is an acidic lake. Then you get acid rain. You look at the top, you start getting into the citrus juices, orange juice, lemon juice. And then it starts getting really sulfuric acid, battery acid, you know, way at the bottom of the acidic side of the scale. Bananas actually surprised me. I thought they were kind of more alkaline, but they're actually a little bit slightly acidic. Then you go the other, you have milk, you have pure water. So 7 is kind of, you know, right there where pure water is. And then you start getting into seawater, eggs, baking soda. I think that's a medicine for upset stomach. Milk with magnesia. Ammonia, soapy water, bleach. Oh, liquid Drano is way down here at the most alkaline. You don't want to be at the two extremes. All right, so that was just a little something extra at the end of the video. See you.